Okay, where did we stop last class? Numericals. Which chapter? Electromagnetism. Applications. We did transformers. We had completed till where? Of चैप्टर हो गया क्या? Faraday's law, transformer, वो सब हो गया? What did we do? To start with KHR26, which is what topic? Did we do force on current carrying conductor? एक मिनट देखो तो एप्लीकेशन टाइप क्वेश्चन किसके कर रहे थे आप? अच्छा बी हो गया. Okay. So when they are saying I was going to do application based question for what? Okay, so let's complete C also, then we'll get to questions. Okay, let us complete the last part of it. Okay. So DC motor we have done, right? Till DC motor we have done. Till DC motor we have done. Okay. So far we are aware that whenever current flows through the wire, it produces magnetic field errors. Correct? Whenever wire के अंदर से current जाता है, it generates magnetic field errors. That's what we did, right? And we also covered the DC motor, right? And DC motor is the application of force acting on current carrying conductor when it is placed in magnetic field, right? This will help you. We did DC motor in the last class, right? Okay. So electromagnetic induction is opposite of that. Or when there is a magnetic field, okay, around the wire, can it produce current in the wire? Are you understanding? When current produces magnetic field around it, here's the reverse true. Can magnetic field around the wire produce current in it? That's what we are going to explore. Because nature observes symmetry. So if one situation is true, the reverse also must be true. That was the motivation to explore electromagnetic induction. Is she from our class? Okay. So, first let us write down what is this. Whenever magnetic flux Current is induced. It could be coil or loop. Okay. So what I've written on the board is, whenever you have a coil, okay, silence, everybody pay attention here. Whenever you have a coil, right? Let's say there is a coil like this, imagine, and I am bringing a magnet close to it. Okay. So then what happens? The flux linked with the coil changes, and let me draw this diagram. Let us say you have a coil like this. Right? Yes. This is a situation. You have a coil and you are trying to bring a magnet towards it. Let us say in this direction. Right? Then what happens is, this galvanometer shows deflection. What did I say? Whenever you bring a magnet near a coil like this, there is no cell in this. Okay? So there is no source of electric current right now. But the movement of the magnet shows deflection. Okay? So that means, what is happening due to movement of the magnet? So magnet has nothing but magnetic field. Right? Obviously, it is completing the loop. The magnetic field is completing the loop. So when the magnet is moved towards the loop, then what might be happening? The number of field lines passing through the loop is increasing. So this chapter is totally experimental. Try to understand what is happening here. Okay, people at the back, stop the conference. I will make them be silent and pay attention here. Why don't some of you come here? You come here. Parth, both of you, Parth and you both, get up. Come fast. Every class I have to do this to basically. Too much noise coming. Kya hua? Kuch issue? Some crisis? Is there anything I can help? No? Okay. Oh, here we go. कहाँ गायब हो गया था यार? क्लास में से रौनक गायब. यहीं बैठो, इधर आओ. हाँ, यहीं बैठ जाओ. हाँ. अच्छा, इसको उठा जरा मोक्ष, अपने बाजू वाले. तू भी आ जा मोक्ष. Come here. Come here, come here. You want to come? No, no. हाँ, okay, you come. You are the main person. Come. I'm making space for you. Come here. Come here. You get up. Come here.
Under bed.
Hmm?
Under bed.
Under bed. All tall people sit on one side. Pratyush, don't sit on. इसको क्यों अंदर भेज रहे हैं?
सर वो दिखेगा नहीं बोर्ड.
किसे नहीं दिखेगा? इससे नहीं दिखेगा चलेगा?
मुझे नहीं दिखेगा.
ऐसा क्यों करना पड़ता है मुझे? तुम लोग को जब तक शेक नहीं करो शांत नहीं करो. Okay. So the noise index is still more on this side. What's going on? Okay. So what did I just display on the board? Just read the description and explain what is happening there. So what we are observing is, whenever the magnet is moved towards the loop, the galvanometer attached in the circuit shows reflection. Now when galvanometer shows reflection? Whenever there is a current. So there is something associated with the motion of the magnet and the current generated in the loop. Is there any cell in the loop? Is there any cell or source of current connected in the loop? No. Still, current is generated. That means there is something to do with the motion of the magnet with respect to the coil. So what changes when the magnet is moving? And the current, the galvanometer shows deflection only when the magnet is moving either towards the loop or away from the loop. So when it moves towards the loop, the deflection shown is in one direction. And when it moves away from the loop, the deflection changes. The direction is opposite that. And if the motion is fast, deflection is more. If the motion is less, deflection is also less. So, what is changing due to the motion of the magnet? If you observe carefully, look at these lines. When the magnet is far away, these two lines will not cross the loop. Okay? Whereas these three will. Right? When the magnet comes closer, all these lines will enter through the loop. You get it? So this magnetic field lines, these are called magnetic flux. What is magnetic flux? So magnetic flux, it is represented by this, is the number of field lines, number of magnetic field lines. Crossing unit perpendicular area. Okay, what is magnetic flux? It is the number of magnetic field lines crossing unit perpendicular area. Like if this is the area, so let us say when the coil is like this, right? So these two lines will pass for sure, but when I come closer, all four will pass through. Okay, but when I am far away, these upper and lower lines will miss the loop. Okay, so this is the meaning. Whenever magnetic flux linked with a coil changes, an EMF and hence current is induced in the coil. This process is called electromagnetic induction. So all you need to do is change the magnetic flux through the coil to produce current in it. This is the principle on which AC generator works. How do we generate electricity? By changing magnetic flux through the current loop, which we call armature coil.
So this diagram, the three lines, those three lines will be assumed to be the magnetic flux.
These three lines?
Will be the magnetic flux and the other ones.
Yes, the magnetic flux is this. The number of field lines. Let's say there is a unit perpendicular area like this. So the magnetic flux is 1, 2, 3, 4. Flux is the number of line which is penetrating through unit perpendicular cross sectional area.
It must meet the loop.
Has to be in the loop. Only then in that wire current will be generated. So this is the reverse phenomena. Like when there is current in the wire, it generates magnetic field. Now current is charge in motion, right? Current is nothing but charges in motion. So charges in motion create magnetic field around it. Now a magnet in motion puts charges back in motion. You understand? So it is the reverse phenomenon. Understood? So this is called electromagnetic induction. So how to detect the direction of induced current? How to detect the direction of induced current? That should be the question. Like current is generated, but in which direction? So what we observe is when the magnet is brought closer, right? When the magnet is brought closer, the deflection is in this direction. Towards right. Okay? So if the deflection is in this direction. Understood? And when the magnet is moved back, the deflection is on the opposite side. So when you look from this side, what kind of current is being produced? Anti-clock. This is the left side. Left and right. This is left and this is right. When you look from this direction, left of the coil is this. So in the left side current is going up and in the right side current is going down. Are you with me?
Sir, it's the Fleming's rule then it should be fixed towards.
First understand what I am trying to say. We'll come to Fleming's rule. How to detect the direction of induced current? What did I say? When the magnet is coming closer to it, it shows deflection in the right direction. When you see deflection in the right direction, that means current direction must be like this. Okay? So, this is the back of the coil when I am looking from this side. To me, it is appearing south. But this is back side of the coil. This is back side, right? Where is the galvanometer? To the back side. So when the magnet is coming from this side, when I see south, this side must be north, isn't it? What is this side? This must be north. The coil that you are seeing on the board is like this. Okay? The coil that you are seeing on the board is like this. So magnet is coming in this way. Okay? So what we are seeing on the board is the back. Back is this side. This is the back side where the galvanometer is kept. So when the magnet is coming here, the north pole is approaching here, right? The current is set up. Now this is a rule. Current in the coil will be set up in such a way so that it opposes the coming closer of the magnet towards it. So this side should be, due to the induced current, it will develop north pole. You understand? Because you have to do work against the force of repulsion due to the generated current. To follow the law of conservation of energy. If it does not happen that way, that means you are generating energy without any work. Are you getting it? So this is nothing but somebody is doing mechanical work in moving the magnet, and that mechanical work is converted into electrical energy of the coil. Making sense? Little deep. Okay, read this statement. So, direction of the direction is given by a law called Lenz's law. Lenz's law. induced in the coil is such that the direction of induced current in the coil is such that it opposes the cause. Does it make sense?
This diagram, the current is going 90. So how is it solved? The current is going 90.
I am saying this is south. What is it for you?
For me, this is
That's what is happening here.
so but
What you are seeing is the galvanometer side. The magnet side is this.
south.
From the magnet side it is north.
So, but
It is north.
I'm saying that for if we look from the value, it is
From this side it will be north.
the magnets was
Okay, but from this side it will be south.
this side should be north, and from the magnets perspective, this side is anti-clockwise, it will be north pole, and the direction
Take
is.
it. When you see from this side it should be north. So, oh, that is clockwise. या तो ऐसे होना चाहिए. ठीक है? So, नहीं मैंने ये डायरेक्शन कैसे बनाया था पहले?
अब क्लॉकवाइज है
तो यहाँ से साउथ दिखेगा. यस, अब ये साउथ दिखेगा.
अब उस साइड से
नॉर्थ. करेक्ट. ठीक है? So good observation.
और एक चीज ये बस थियोरेटिकल क्वेश्चन है जो हमने पढ़ा था कि सॉफ्ट आयरन का बार लेते हैं
तो थोड़ा जोर से बोल रहे वहाँ से इतना जोर से.
सॉफ्ट आयरन का बार है इधर मैग्नेट है तो if this side is the north pole then wasn't it that this side becomes the south pole
Yes.
but इधर देखें इस साइड से ऑपोजिट जो साइड फेस कर रहा है वो नॉर्थ पोल बन रहा है इधर भी वो नॉर्थ.
ये साइड नॉर्थ बन रहा है. ये साइड.
हाँ that is the side closer to the
तो इसीलिए तो उसको रिपेल करेगा ना. नॉर्थ आ रहा है तो यहाँ नॉर्थ बनना चाहिए. नॉर्थ बनने के लिए इट इज एंटी क्लॉकवाइज करेक्ट फ्रॉम दिस साइड. ओके, लेट मी रीड्रॉ द डायग्राम. ओके, ये थोड़ा सा कंफ्यूजिंग हो रहा है. अगर हम इसको ऐसे बनाएं let us say the magnet is now coming from this side. And it has to generate north pole to repel it. तो कैसा हो? अभी कैसे जा रहा है? ये ऐसे है. Is it clear now? This face is facing the magnet now. So you have to only understand the direction of induced current in the coil is such that it opposes the cause of it. What is causing this current? The changing magnetic flux. So there is a law, the EMF induced is equal to rate of change of flux. What is the EMF? It is equal to rate of change of flux. Like if you move it fast, d phi by dt will be more. Okay? This is nothing but Faraday's law. This is Faraday's law of electromagnetic induction, written mathematically. Okay, and then what is Lenz's law? You have to put a minus sign. This negative sign means EMF, the direction of EMF, and hence the current is such that it opposes the rate of change of flux. So how will you oppose this rate of change of flux? By producing reverse flux due to the induced current. So induced current will now repel the magnet. See, this induced current will create its own magnet, and like poles will repel. So that's how it is easy. Mathematically it is expressed like this.
The second doubt I was having was that in 9th standard we learned for soft iron bars, when you bring a magnet close to it from magnetic induction, the opposite pole is created on the
That is induction. That's magnetic induction. That's different. Because of that, it attracts
So
it.
there it will be attraction.
Yes, that is different. That is induction of magnetic field. That's magnetic induction. Here it is electromagnetic induction. You understand? What is it? Electromagnetic induction. Is this clear? You need to only understand this concept. What is the concept? Whenever the magnetic flux through the loop changes, if this is confusing, okay, just drop it. Anybody has a kada or bangle? Give me your ID wala. ये दे. kada है किसी के पास नहीं. Let's say this is the loop, okay, and this is a loop, okay, and a magnet is being brought here. Let's say this is the north pole. This side is north pole. Here I write south. So what pole is this? North pole, okay? And this is a coil. Now I have to stand in one corner so that everybody gets the same view. The whole class is getting the same view, right? So this is the face of the coil. Imagine this is circular loop. Now this north pole is coming this side. So in this, a north pole should be generated to oppose this magnet from coming closer. Only then I have to do work now. If there is no opposition, that means the current is produced on its own. ऐसा नहीं होगा, ठीक है? So because this is north pole, this also should develop a north polarity. So north polarity means it will develop a anti-clockwise current. This is the funda. So who is giving the direction of induced current? Negative sign. And what this negative sign does? So rate of change of flux is taking place due to the motion of the magnet. Okay? And because of that, the current produced now opposes the coming closer of the magnet. Means now the induced current is opposing this. This is the meaning. So this is 2-in-1 law. One is rate of change of flux, which is responsible for electromagnetic induction, and this gives the direction of the induced current. Is that clear? Okay? So if I do this fast, the induced current will be more. The magnitude is more because of this. Okay? And this anyway will give the direction. So now tell me, which pole is developed? You have to tell me what is the pole getting developed here. So this is north pole coming here. South, north, south. Because north, when it is going away, current will reverse now. So that it develops south, so that now it opposes going back of the magnet. You understand? So if you keep moving it like this, the current is changing direction, north, south, north, south. That is why alternating current. Okay? You understand? There is one more law which gives the direction of induced current, right? Which is called Fleming's right-hand rule. Another law is, this is basically Faraday's law. This is Faraday's law of electromagnetic induction. This part. Okay? And this is due to Lenz's law. Lenz's law gives the direction of induced current. Okay? Now, when Lenz's law is applicable, magnet in motion, coil is इसलिए कौन सा सवाल है? नहीं, अभी क्लास डिस्टर्ब होगी, पहले ये समझो उसको। तो अभी हमने क्या सीखा? लेंस लॉ क्या देता है? What does Lenz law give you? What does Lenz law give you? Direction of the induced current, and it is also direction of the induced EMF. मतलब what follows current? EMF or current follows EMF? Current follows EMF. तो मतलब पहले EMF generate होगा and then current will follow. Understood? So it is the direction of induced EMF and hence current. ठीक है? Now what is the other situation could be the magnet is kept stationary. Is there any way I can change the flux through the coil? What is the situation you saw just now? Coil stationary, magnet is in motion, and because of the motion of the magnet, the flux is changing. Is there any other way by which I can change the flux through the coil by keeping the magnet stationary? Move the coil. So move the coil. Yes, you can do that. You can do that. Any other way? Huh? There's one more way. Let us say I have a magnet here and this coil is mounted on an axis. Coil is mounted on an axis, right? So let's say this is a coil, this palm is a coil, okay? So, and this is the magnet. If I rotate the coil like this, is flux changing? If I keep on rotating in one direction, will the flux change through the coil? It will change all the time. Right now, all four lines are passing. Now, reducing, reducing, reducing. In this orientation, Parth, क्या बताया मैंने अभी? क्या हो गया तेरे बैग में? So this coil, when it is perpendicular to the magnetic flux, all the flux is passing through it. Now when you rotate it, what is happening? Is the flux, number of lines passing, reducing? Right now, zero flux. Okay? Again it is increasing. So if I keep rotating the coil, it's a very convenient way to change the flux. And I'll get the same result. Due to changing flux, current will be generated in the coil. Understood? So this is what will be used, this concept will be used, okay, to create AC generator. Okay, if you understand this concept, so in AC generator, this is how we'll change the current in the coil. This is how we'll change the flux in the coil. Okay, so when the magnet is stationary and the coil is rotating or coil is in motion, that time the direction of current is given by Fleming's right hand rule. Which rule? Fleming's right hand rule. You have already learned Fleming's left hand rule. That was used where? To give the direction of force acting on current carrying wire placed in the magnetic field. What was that rule? Fleming's left hand rule? It gives the direction of force acting on current carrying wire placed in the magnetic field, where the direction of magnetic field and current may be known. Then you can figure out the direction of force acting on the wire by aligning these two directions. Now what is Fleming's right hand rule? Exactly like Fleming's left hand rule, but here it will give the direction of induced current. The roles of the fingers are same. Now force is applied on the coil, because coil will not rotate on its own. You have to now apply the force on the coil to rotate it. So force is known. Magnetic field direction is known. So these two things are known. So this gives, the middle finger will give the direction of induced current. Is that clear? So when we discuss AC generator, that time the rule of, how to apply right hand rule, that will become clear. Okay? So we'll now go to study AC generator. Okay, now go take your bag. When I'm explaining anything, do you think it's just story? You don't need to focus on that? Concept नहीं समझेगा तो तुम्हें कुछ भी नहीं समझेगा आगे. Whole academic year is coming to an end and you are still figuring out how to study physics. जा लेके आओ भी bag. I'll start after that.
This example, what is the direction of the force?
What is the
direction of the force produced? With the repulsion.
What is the direction of the force produced? Where?
In that direction. Repulsion.
Direction of force is known because I am turning the coil, right? So I know what is the direction of force. Here you are moving the magnet. So which pole is approaching north? North will be repelled by north only. So here the current will be induced in such a way that north pole is generated when the magnet is approaching. Then only there will be repulsion. That is not the force in the right hand. Fleming वाला वो सब नहीं कर रहे अपन यहाँ पे फिलहाल. Keep it separate. हाँ, इसको lens law से approach करो. Lens. That's what I'm saying in AC generator. So when we draw the diagram of AC generator, the coil will be rectangular. There it will be easy to understand. It will work in circular coil also. Basically, it's the same, but it is better to understand with the rectangular coil. Okay? So what have we understood so far? We have understood what is electromagnetic induction, and we have understood how to figure out the direction of induced current. Okay? Have you understood both of them? So what is electromagnetic induction? Who would like to explain? Everything is on the board. The question I'm asking is on the board. Raise your hand and answer. Nobody is raising the hand. So shall I choose somebody? तो समझ गया ना आगे बढ़. Would you like to answer? Yes? Try. लिखोगे कैसे तुम लोग? Would you like to try? मतलब किसी को समझ ही नहीं आया? देखो ये होता है क्लास के बीच में बैग लाने से ये होता है किसी को कुछ समझ नहीं आया. बहुत सिंपल है. अगर किसी भी कॉइल या लूप में मैग्नेटिक फ्लक्स चेंज हो रहा है विथ टाइम, ठीक है, और जैसे ये मैं मैग्नेट को ऐसे लेके आ रहा हूँ तो ये डिफ्लेक्शन दिखा रहा है, मैं रुक गया तो डिफ्लेक्शन जीरो हो जाएगा. क्यों? मैग्नेट जैसे ही स्टेशनरी हुआ फ्लक्स चेंज होना बंद हो गया, और जैसे ही मैंने मैग्नेट फिर से मूव करना शुरू किया फिर से डिफ्लेक्शन दिखा रहा है, मतलब करंट फिर से आ गया सर्किट में. यही लॉ है. इट्स ए नेचुरल फिनोमेना. व्हेनेवर मैग्नेटिक फ्लक्स थ्रू अ कॉइल चेंजेस इट जनरेट्स करंट. जनरेट. It's a natural phenomena. Understood? Just like when you rub your hand on a surface, you feel warmth. It's a natural phenomenon. वैसे ही ये electromagnetic phenomena. Whenever a magnetic field or a magnetic flux passing through the coil changes, it will generate current in it. Just like when a current flowing through the wire generates magnetic field around. Increase the magnitude of current, the magnetic field strength increases. तो ये electromagnetic phenomena है. ठीक है? So store this in your head. कि कभी भी मैग्नेटिक फ्लक्स जब चेंज होगा कॉइल से तो उसमें करंट जनरेट होगा, जनरेट हो रहा है इसीलिए उसको हम इंडक्शन बोल रहे हैं, इंड्यूस्ड प्रोड्यूस, पैदा हो रहा है, ठीक है, क्योंकि इसमें कोई सेल तो है नहीं, देयर इज नो सोर्स ऑफ एनर्जी, तो ये करंट कैसे जनरेट हो रहा है, ड्यू टू चेंजिंग फ्लक्स, ये एक बात हो गया, इसी को बोलते हैं इलेक्ट्रोमैग्नेटिक इंडक्शन, करंट है तो इलेक्ट्रिक करंट है और ये मैग्नेट की वजह से प्रोड्यूस हो रहा है, इसलिए इलेक्ट्रोमैग्नेटिक इंडक्शन, ठीक है। अब वो करंट का डायरेक्शन वो हमें देता है लेंस लॉ, राइट, करंट तो एक डायरेक्शन में फ्लो होगा, हाई पोटेंशियल टू लो पोटेंशियल, लेकिन यहां तो सेल है नहीं, पोटेंशियल डिफरेंस बताने के लिए वी डोंट हैव अ सेल, so what is the observation is whenever we move this magnet over here it deflects in a certain direction, मतलब it gives एंटी क्लॉकवाइज करंट, डिफ्लेक्शन से पता चल जाएगा ना इसमें करंट क्या सेटअप हो रहा है, एंटी क्लॉकवाइज, तो ये भी नॉर्थ पोल है, मतलब इसमें क्या हो रहा है, नॉर्थ पोल, दिस इज एक्सपेरिमेंटल ऑब्जर्वेशन, द डायरेक्शन ऑफ करंट इज सच दैट when the north pole is approaching it develops a north pole so that it opposes it, and when it is the magnet is receded backwards then the direction changes, reverses, so therefore a south pole is developed. In short, this is electromagnetic induction, okay, and the direction is Lenz's law. Mathematically it is written like this, and this is nothing but Faraday's law. So what Faraday said, the EMF induced in the loop is equal to the rate of change of the magnetic flux with time, okay, so if the flux change is 0, if delta phi is 0, then E becomes 0 immediately, so it has to change all the time for continuous production of electricity, okay. Now let us see how the AC generator works on the principle of electromagnetic induction. Let's see. Ditto diagram has DC motor with small changes. So what was DC motor? You had a magnet, then you had a coil, and the other pole of the magnet. Again, now here you had used split ring, right? Only one split ring was used in case of DC motor. Now here you will use 2 rings. There is no electrical contact between this ring. You have another ring. Again, so this wire is coming through this ring S1. We'll call this as S1. Right? And now we'll draw the induced current with the help of brushes. This is B1. So AC voltage will be created across this resistance as the potential difference across this resistance. Okay. So how the current will be generated? Let us understand. So what is the magnetic field direction? It is here. Again, there is the magnetic field. The coil is mounted on the axis. Okay, let's imagine this is the axis. Okay, this is our. And now we are rotating this coil. Let us say the coil is rotated due to the falling water. If it is a hydel power plant, the water will be continuously made to fall on the some arrangement so that this coil will now rotate like this. Right? So now the coil is continuously rotating. So we'll build dams to have the water capacity so that round the year capacity of water is maintained. So that when it falls, it continuously rotates the coil. So it's not some human rotating. How long you will do? We need some natural process to rotate the coil. Now, so what is the force acting on the coil? Let's consider this point. Force is in this direction. Magnetic field is in this direction. Right? So right hand, Fleming's right hand rule. How to apply? So where is the force? Down. Field in this direction. So where is the current now? Current is coming towards U. So if I call this as ABCD, so current is this side. So it is drawn from B2. Okay? And on this side, if the coil is rotating clockwise, the force is upward. So I know the direction of force and magnetic field. Where is magnetic field? Here. So where will be the current now? B is magnetic field. That's a notation. It's a vector. Not this B.
So the direction will be towards the pole, right? From our perspective.
North to south. North pole to south pole.
So I'm correct. That's all.
Here. B this side at this point. See, you are seeing the coil like this, but the coil is like this. So this is A, B, C, D. 3D, right? So this is A to B. Now, where is B? B this side. Force up. So where is the direction of current? A to B. You get it? So now see, the direction of the current here should be like this. That means it matches. Understood? It matches. Like, so coil is rotated in one direction only. So what happens after 180 degrees? So what is S1 and S2? These are slip rings. To draw. Use that.
Slip ring or split ring?
Slip ring. These two are slip rings. This is DC motor. This is AC. This is AC. ये स्लिप रिंग है ना, स्लिप हो रहा है ना ब्रश के ऊपर. इट्स जस्ट प्रोवाइडिंग द इलेक्ट्रिकल कांटेक्ट. अरे भाई ये सिर्फ एक कांटेक्ट है. ये और इस पे रिंग ऐसे स्लिप हो रहा है, अगर इसको वेल्ड कर दोगे तो तोड़ देगा, पूरा चला गया। इट इज जस्ट अ पॉइंट ऑफ कॉन्टेक्ट टू ड्रॉ द करंट। ये जो करंट इसमें जनरेट हो रहा है बाहर कैसे लाएगा?
और वो ब्रश करंट को रिसीव करता है।
Yes, this brush gives the electrical contact. It is also part of DC motor. तो यही तो मैजिक है। देखो पहले करंट, ये जो करंट आया वो यहाँ से इधर आया, फिर रजिस्टर में एंटर हुआ, दिस इज हाउ, अब S1 में एंटर हो गया इधर, मतलब दिस इज हाउ द सर्किट इज कंप्लीट। नाउ यहाँ पे जो पोटेंशियल ड्रॉप है वो है IR। IR V is equal to IR, वही AC वोल्टेज है। The potential drop generated across R is the AC voltage. Now, what is the nature of AC voltage? ऐसे आएगा, current is constantly changing direction। देखो अगर ये 0 डिग्री है, ये क्या है तुम्हारा π/2, ये क्या हुआ पाई, ये क्या हुआ 3π/2, ये हुआ 2π। After 180 degree, the direction of current is changing. Let's say if I call this positive direction, this is negative. Working is not, you are not supposed to explain the working in the exam. But what is expected from you is how to apply Fleming's right hand rule to predict the direction of induced current. बुक में बहुत कुछ एक्स्ट्रा दिया हुआ है. I will tell you the working. Okay? अब देखो, why the current is maximum at 90 degree rotation. ठीक है, तो इसमें सबसे पहले, although you are seeing the coil as flat, in the diagram you are seeing the coil as flat, तो ये easy है समझने के लिए, but actually में coil को flat नहीं रखते हैं, coil को ऐसे रखते हैं vertical, ठीक है। So शुरू में initial position of the coil is like this, ऐसे है। This is 0, this is 0 degree, ठीक है। अब वो जब 90 डिग्री टर्न होगा तो कैसे आ जाएगा, ऐसे आएगा, तो ये आएगा, दिस इज द सेकंड पोजीशन। ठीक है, ये किस पे है, 90 पे। फिर 180 पे क्या होगा, इतना समझते हैं पहले, ठीक है। तो ये कितना लाइन है, 1 2 3 4 5 6, ठीक है। पूरा 6 लाइन पास होगा कि नहीं यहाँ से, तो ये होगा तुम्हारा 5-1, 0 पे पूरा फ्लक्स पास हो रहा है। आफ्टर 90 डिग्री क्या हो गया, ये हो गया 5-2, ये हो गया 0, ठीक है। मतलब फुल वैल्यू माइनस 0, व्हाट इज चेंज इन फ्लक्स, मैक्सिमम, maximum, so maximum EMF is induced, this is maximum EMF, understood। जब वो 0 से 0 एंगल से 90 टर्न हुआ तो क्या हुआ, चेंज इन फ्लक्स क्या हो गया, मैक्सिमम। तो जो करंट जनरेट हुआ या EMF जनरेट हुआ वो क्या हो गया, मैक्सिमम, पीक वैल्यू आ गया। फ्लक्स इज चेंजिंग ऑल द टाइम, लाइक व्हेन द कॉइल इज रोटेटिंग, flux is reducing, so changing, reducing, maximum reduction। तो थोड़ा थोड़ा चेंज जब तक हो रहा था तो थोड़ा थोड़ा EMF जनरेट हुआ था, मैक्सिमम चेंज जब हुआ तो मैक्सिमम EMF जनरेट हुआ, बिकॉज इट इज डायरेक्टली प्रोपोर्शनल, फैराडेज लॉ, ठीक। अब जब 90 के बाद वो 180 पे जा रहा है तो क्या हो रहा है, वापस से थोड़ा थोड़ा फ्लक्स एंटर होने लग गया। व्हाट इज द डिफरेंस विद रिस्पेक्ट टू इनिशियल डायरेक्शन, नाउ व्हाट इज द डिफरेंस, 0। change of flux becomes 0 at 180 degree. पहले जा रहा था 5-1, फिर से 5-1 जा रहा है, तो चेंज क्या हुआ? 0. ठीक है, तो इस केस में क्या हो गया? वापस से ईएमएफ क्या हुआ? रिड्यूस होते होते क्या हो गया? 0 हो गया. ठीक है, अब उसके बाद एक और टर्न लिया उसने, तो क्या हो जाएगा? ये हो जाएगा तुम्हारा डीसी, ये हो जाएगा एबी. क्या हो गया? एबी इधर आ गया और सीडी इधर आ गया. ठीक है, तो अब जो करंट डायरेक्शन है, पहले ए से बी जा रहा था जब ए बी इधर था. ए बी जब इधर था तो डायरेक्शन क्या था? ए से बी. अब जब ए बी इधर आ गया तो यहाँ पे तो फ्लेमिंग्स राइट हैंड रूल लगाओगे तो करंट इधर ही आने वाला है. जो भी साइड इधर होगा करंट विल ऑलवेज फ्लो फ्रॉम टॉप टू डाउन. तो अभी क्या होगा? बी से ए की तरफ करंट आ जाएगा जैसे ही ए बी इधर आए. इस केस में करंट इज नाउ दिस. पहले कैसा करंट था यहाँ पे? सेम डायरेक्शन है. पहले ए टू बी था, आफ्टर 180 डिग्री क्या हो गया? बी टू ए. तो यहां से अब जो करंट डायरेक्शन है वो क्या हो जाएगा? उल्टा हो जाएगा, उल्टा. एंड देन नेक्स्ट रोटेट, ये रोटेट हो, अभी आगे यही सेम चीज क्या होगी? रिपीट होगी. आफ्टर एवरी 180 डिग्री रोटेशन the current direction is changing, the magnitude is increasing now in the opposite direction. ठीक है, और ऐसा हम 50 टाइम्स करते हैं. जो हमारे घर में सप्लाई आती है वो 1 मिनट में 50 टाइम्स डायरेक्शन चेंज करती है. और ये जो ईएमएफ है ये कितना आता है? 220 वोल्ट. 1 सेकेंड 220 वोल्ट एसी. अंडरस्टूड? तो ये है, लेकिन ये वर्किंग तुमको नहीं है, तुम्हारे को सिर्फ हाउ टू अप्लाई फ्लेमिंग्स राइट हैंड रूल. आस्क हिम नॉट टू इरेज द डायग्राम. विल कंटिन्यू आफ्टर द ब्रेक. ब्रेक इज फॉर अस आल्सो 10 मिनट्स का. वी स्टार्टेड एट 5:25 राइट. ये वाला थोड़ा शॉर्ट एंड क्लास है. So I'm leaving the volume here.
Good.